Now record start. So for the rest of this topic will be about the types of model. Yeah, the common types of model. And I'll put this way. Usually, these types of model only help you with sometimes knowing the advantages and disadvantages of picking a type of a model, or maybe picking a choice of your tool. It's more like that. And many times these I should say first, like when we divide the model types according to function, you can separate it into two types. Let's say it could be parametric or non-parametric types of model. If you separate these model with learning methods, then maybe you will end up with supervised learning, unsupervised learning, and self-supervised learning. If you separate them according to task, it's kind of like what the model is built for. Just say YOLO 8 is built for object detection, stuff like that, or I'm not sure, but yeah, it's, or maybe VGG is a deep learning model that's initially improved for classification. Yeah, so stuff like this is like just the application of that model. And lastly, you can also define the type of your model using Bayesian equation. And for that, you will also end up with, let's say, generative model, discriminative model, and conditional generative model. And probably you already heard about the generative and discriminative. What I described previously is more like a nature of how it operates. But this one, we will look at the Bayesian equation and kind of like link that equation to the explanation. But this is more like for you to know what people are talking about when they talk about the machine learning. Yeah. Probably I think I wouldn't ask like what types of this model, because sometimes even for myself, I can get really confused by that, because sometimes, let's say when we talk about ChatGPT, right? ChatGPT is a generative model. Okay, you tick this one. It's a generative model. It's used for, let's say, very close to recovery, but it's like reconstructing an image. And usually this generative type will require both most of the time it requires the supervised learning because you need a label. But sometimes if the data structure can help you learn that generative task, sometimes unsupervised learning could help. And then when we talk about using generative model that came from deep learning, that is a non-parametric function. So you can see the overlap between the definition, especially when it comes to the types of model based on the learning method. You can have more than one. It doesn't always just one types. Let's say recently we have a classification model that's actually rely on unsupervised learning. It uses a pattern of the feature vector. Let's say if the vector belongs to the image of the same types, then it will exhibit something like orthogonality. So these types of behavior or maybe characteristics can be, exploited in the unsupervised learning. But you can also use the labeling to support it. So it's like the difference between them may not be as clear as we wish it to be. But for the very fundamental machine learning techniques, usually you have a clear separation. For example, most of our model that we would learn in this course are both parametric and non-parametric. And most of them will be learned with supervised learning. And all of them will be done for discriminative task. Like that. Okay. But yes, some of them, especially the clustering algorithm, are unsupervised. Learning could be done in unsupervised way. Yep. And the task that we will do is classification, regression, and clustering, which I haven't put it in here, but that's like the third one, the last one that we will learn before final. Okay, let's start. So what's the parametric and non-parametric model? I think my description here, okay, I actually provide some description in these slides, but even for myself, I find it's very tedious to read. I'll put it very simple. If a model is a parametric model, it usually have assumption about data distribution. Or they have some assumption about the formulation. Let's say our previously linear regression is actually a parametric model because it's assumed the linear relationship between parameter and the inputs. So linear regression, logistic regression is very similar to linear regression, except that after you perform the vector production between input and your model parameters, then you give this as an input to a sigmoid function. And your result will be like a y hat, but this y hat will be having a value between 0 and 1. But the thing is, usually they will use this model for a classification task because the way the sigmoid function map your output model will be something kind of like this. So it has like a very strong period for 0, and then you will have some kind of transition and you go to 1. And usually you have a thresholding value of 0.5, and then you say if it has a value beyond 0.5, that is class 1. If it's lower than 0.5, then it's class 0. So usually this logistic regression is like a classification task, but it's of course assume the relationship between model parameters, and it's assumed that that can be mapped well with sigmoid function, the decision, the binary decision. Naive Bayes is another parametric method, but the assumption that is made on the fact that there are independency between features, and I'm not sure, but maybe we have to look at it. Some of it also rely on the assumption of data distribution, such as it's a Gaussian distribution, distributed data, something like that, but I'm not sure. But usually if it's around here, it has this kind of assumption. Hidden Markov model, probably this have some assumption about the independency between your connection, your data connection that has to be tree-based, connected, and there's some transition which you have to say is conditional on just the sample before it, like they have Bayesian stationary assumption, stuff like that. So simply put it, when there are assumptions about your data, and when there are assumptions about the formulation between your input and parameters, either one of them, just one of them, then it's a parametric model or parametric method. On the other hand, if you don't have any of those assumptions, distribution free, and no assumption about the formulation between inputs and your function, then it will be classified as the non-parametric method. Let's say k nearest neighbors. Pretty much when you do k nearest neighbor, you use a distant function, then you say whatever close to me up to k samples, you're classified as my group, right? Or support vector machine where you have a hyperplane, say that this hyperplane has to divide between two groups, or maybe your hyperplane could be nonlinear. But as you can see, these methods are not totally assumption free. There's still some kind of assumption. Let's say for support vector machine, you have actually two types, roughly. The one where you separate it with a linear hyperplane, and the one where you separate it with a kernel function. The kernel function will allow the separation to be somewhat nonlinear. Or sometimes if you have like a slack variable to help with your separation, you may say that your separation is going to be made with some soft decision, which allows some misclassification. Let's say if those data samples are interfered with noise. So there are a certain level of assumption. But usually the common thing among these methods are the fact that they are distribution free. Neural networks can be formed similar to linear regression and logistic regression. Actually, you can use neural network to do these two things. Because neural networks composed of model parameters, but when we call it neural network, a deep neural network, it usually means that you have, let's say, a linear model of input, and then you feed that linear model as an input of another layer of linear input, and then eventually it becomes like a nonlinear mapping. So that's kind of a reason why we call neural network as a non-parametric, because it depends on how deep you want it to be. But when you map it with a very deep layers or many layers, the assumption about data distribution is gone. Like you don't care about it anymore. You just want this model to be able to give the output that it has to be when it learns with your training data. So that's the reason why it's classified as non-parametric. So yes, anything distribution free, anything with lack of assumption, non-parametric methods. That's it. And these are examples. And we will learn all of them except the hidden Markov model in this course. So yes, so if you still interested in this course, we will learn all of that. We go through all of that, except the hidden Markov model, because this one is pretty much useful for the like a time. It's like you have to have some kind of transition between events or stages. But in our situation, we are not considered any sequential task like that. Usually our task is like given an input, produce an output. Just that, yeah. Okay, so pretty much I believe that whatever I just said cover all of these, so we can skip. And okay, lastly, what is the benefit, maybe positive things and the negative things about parametrics and non-parametrics method? And probably this will give you an answer maybe to some of you if you ever have a question of, if deep learning can do anything, I mean, pretty much, why we still need to learn the mathematical model? Okay, the answer is simply, if your model fit your, let's say, your data assumption, your assumption about your system fit exactly to your reality, the parametric model will work much better than deep learning or neural network. That's like a first bullet here. When your assumptions met, that model is going to work better, not only in terms of performance, but also in terms of computational complexity. When you have to train machine learning or deep learning, that is, with a lot of layers, you have to train it. That's one resources. And when you do the inference, if your model is very deep, your inference time will be longer than if you were to find a mathematical model that fit your assumption. That mathematical model that fit your assumption will, of course, use less parameters and then use less training sample, and then when it runs inference, it will perform faster. So that is the clear, like the very clear benefit of parametric model. But the drawback also, if your assumption went wrong, or if your whatever assumption that you made about your system is very limited, it's not really flexible, I would say, just that way. And yes, when your assumption is too simple, it then will not be able to capture the complex relationship. So that's something to be aware of if you were to use like a parametric method. And that drawbacks of parametric method is something that non-parametric method doesn't have. Let's say it's widely applicable, it's easy to implement, just like what we say these days, everyone can learn and train machine learning, deep learning neural network, without knowing what they're doing. Pretty much it's like that. If you have a target label and you have input and your data is large enough, you can train it. That's why it's very much easy to implement. And that's like one of the benefits. And also if your data or maybe your model will have to handle lots of outliers. Most of the time, it's proven that the non-parametric methods are more robust to outlier. Because outliers are those that doesn't fit the data assumption. On the other hand, the parametric method will be very sensitive to the outlier. It will fail if your outlier just happened and you didn't aware of it. So you can see it's like the negative side of parametric method is something that is the positive side of the non-parametric method. And vice versa, for the negative stuff of the non-parametric method is actually, could be fixed by the positive stuff of your parametric model. So all of these are reflection of each other. Yep. Done. We done the first part. Any question? No? Everything's still simple?
When you are talking about the robustness of the class, the advantage of non-parametric, the best bullet. Yeah, this one.
This one? Robust to outliers?
Yeah.
Usually when we have data samples, right? As I mentioned before, there are training, validation, and testing. Sometimes it's difficult to define which data is the true noiseless samples and which data is interfered with noise. And when that happens, neural network or maybe the non-parametric model will use the majority of the data to help you make that decision. So it's pure data driven. In that case, it doesn't care which one is outliers. It just match with respect to the majority. So in this sense, it's kind of robust. But if we think about the parametric model compared to parametric model will make a decision based on your rules. And if your rules does not include that outliers, or you didn't aware of that possible noises, very likely your rules will be broken by those outliers. So that's why we say that the non-parametric model tend to be more robust to noise, to outliers. Shall we go? Okay, so we come to this learning method and then we will probably finish with the Bayesian. Yep. And then we take a break and then we come another 1 or 2 lecture and that's it. Okay, so the next one is the learning methods. This is like another way to separate your machine learning model. Okay, first of all, I think I have to make it clear for one thing. every methods that we talk about here are those that require a training phase, which means that, of course, if you have an algorithm that performs something like average, let's say, that method receive inputs, compute the average of your data sample, and return that average value as the output. These types of method is not learning method because it doesn't require to learn anything. It just given an input, it computes something, it gives an output. So I would just confirm that these aren't the method that we're considering here. Those methods, usually we refer it as estimation model. So it just performs estimation. But the term estimation itself covers lots of things, including learning method. So when we say learning, pretty much it means that we really need to learn it in order to estimate the model parameters. And once we have model parameters, we will use it in our deployment or maybe testing it. Yeah. Okay, now the next thing is, what if we were to separate these model based on how it learns the model parameters? I guess that most of us are used to this type of learning that is called supervised learning, which means when we refer to supervised learning, one thing that it needs to have in this learning system is the label or ground truth reference. If you have ground truth reference or labels, then it's a supervised learning. Yep, that's it, just the label. And it doesn't need, the learning algorithm, which is formulated as this optimization problem, it has this cost function, the least square function. This least square doesn't need to be like your default types of functions. You can use other types of functions to perform the learning as well. Let's say you can change from L2 norm to L1 norm. Maybe I'll just use this like that to make it clear. Like you can do it this way as well. It depends on your situation. Usually when you use the L1 norm instead of the, let's say, square norm or maybe L2 norm, it's suggesting that you are aware of the fact that there are high outliers in your system. But this is more like a side story. It's not a main topic. Anyway, what types of maybe applications that people normally learn the model with the supervised learning? Well, the answer are the regression task, classification task. Actually, support vector machine is a classification task, but I kind of put it here. Actually, many types of machine learning model will use supervised learning because most of them will have some kind of reference, and when you have the reference to be your label, then that's it, supervised learning. Okay, next is the unsupervised learning. Unsupervised learning is pretty much the opposite of supervised learning, and the opposition of it is the fact that it can train the model without a label. That is, you learn without using any reference. And is that possible? Okay, I'll put this way. It is like learning where you can use an alternative way to create your reference. For example, in this picture, it is a feature matching task or image matching. Image matching is used a lot, especially when you want to identify, let's say, an object of interest in a picture, or you can use it to perform some kind of localization. Let's say if you have a robot that walk into a hall, actually feature matching will be done all the time. or the image matching. They will do that in order to create like a 3D maps of the object that it captured within the camera. So in this feature matching, usually you will have, let's say, image A and image B. Then what you want to do is to match them. You can match them with a single value, or you can match them with the entire features, but in this case they usually match them by using every pixel value in the image. But usually people will not directly use the image. They will encode that image into a feature vector. Let's say in this example, we may have x subscript plus to be the image of A. Then as we fed it into like a deep learning, we may be getting a feature of higher dimension S plus. That is kind of the output of your image into maybe a model or function with the unknown parametric data. And what you want is that you want to match the object that was like this book in image A with this object in image B. So what would happen is that you also have to encode image B. Let's say, okay, sorry, I will use the x negative for the image B. And then we have the s negative as like a feature vector for it. And maybe I'll just make it clear, like this one may be of Rn dimension, this one as well. High dimension feature, stuff like that. So if S plus and S minus contain this similar feature, maybe the dot product between them should be high. And maybe if they are not, let's say if this book is not in this image, then the dot product between that two vectors should maybe close to 0. Then this is like orthogonality property. So sometimes when we learn a model for this type of learning, we will just find the model parameters that encourage the matching of the picture that contain the same object. Okay, I actually wrote it here. So this is actually written, sorry. I'll just put it this way, like it's like S plus, S minus, like a dot product between that two vector. That's it, yeah. So this is like an example of unsupervised learning. There are other tasks like image retrieval. Like when you have to find similarity, usually they use these types of learning. Yeah, they use the orthogonality assumption. Yeah. Okay, lastly, finally we have this self-supervised learning. In the context of self-supervised learning, is actually the context set up in the situation where you may be having a large training samples. Initially, it's kind of set up that way. You have a set of large training samples, but only a few of them are labeled. So it's like you have a large set of data, but only maybe a fraction of it are data with label. So what you did in order to make use of this data could be training a small neural network, or maybe it's a small machine learning. Use this data to train a machine learning. And then once you have a trained machine learning, you use them to infer the rest of your data. So this could be like an ML, machine learning model, where you maybe have few label data, then you get what it's labeled, then you use it to infer the rest of the data to get the label of the data that you haven't labeled yet. So it's like originally these types of learning happen because of this reason. However, later on, people also learn that actually, if we have like a normal training data set, it has label, everything complete. People also found out that if you train maybe a deep learning model or a machine learning with those data, and you want to improve its performance, you can also use this concept of self-supervised learning to improve that model in this way, which is kind of opposite to that. Okay, so firstly, you have like a complete set of training. And then you use that training data to train a very powerful machine learning model or maybe deep learning model. And you use that model to teach a smaller machine learning model with that training data. They found that if you give an input from the powerful machine learning model to that smaller model, even though that output from the powerful machine learning model may not be 100% correct, it helps improving the learning of the small machine learning better. And this concept is called knowledge distillation. Don't worry, it's not going to be on the exam, but it's just like a side knowledge. Usually in these days, the powerful machine learning are the big neural network, like the one with maybe hundreds, millions parameters inside. And they use that to train something very small, like mobile net. This is like another technique to improve the performance of the small model. So if you're interested in deep learning, there are a lot of techniques actually that came out from this concept and idea. Okay, finally, before we're taking a break, is how we may separate the model with the Bayesian function. So there are generative function, generative type, discriminative types, and conditional generative type. This one you can just listen. It's not going to be on exam. It's too advanced. But anyway, I prefer that you know it because we will eventually encounter what we call generative classifier. Generative classifier is a discriminative task, but the way that they train a model will be using generative model. Well, you will see what would I mean based on the Bayesian context. Okay. So first of all, if you can remember Bayesian theorem, and usually the Bayesian theorem, it's going to be formulated in this way. If you have the probability of your data given your label, you can rewritten it using the Bayes theorem, where you instead write the probability of your label given your data multiplying with the prior of your data. We call this one prior. And divided that with the probability of your label. Okay. And eventually you approximate it with just the numerator without the denominator, like you ignore this one. Usually people kind of approximate that way. Okay, and here comes the names. Usually when we talk about the probability of label given data, we call this probability a likelihood function. And for the probability of the data itself, we will call it a prior. And usually this one is called posterior. Okay. With this Bayesian context, any model that derives the output from the prior distribution is called generative model. So it's like, if you imagine that picture of the pets, right? Actually, pets, if we just constrain ourselves to just say we would consider just pets, and we want to just get a sample of pets. So it's like you get a sample from the distribution of the pet's image. So that's generative model. Conditional generative model is when you start to add the condition on the label or maybe on the types of the image that you want to create. Usually this is done in the text-to-image generation. And finally, discriminative model is the one where you want to derive the label from the probability of the label given your model, given your input data. So that is called discriminative model. So it's just this. And this is pretty much more like in illustration of what I just said. Let's say if you want to create like a 3D output of, let's say, a chair, right? You can just asking it to just, give me a view of this chair. Probably the output from this generative model could be various, could be any angle, even the one from the top. But if you are considering conditional generative model, then the types of input output would be different. The input could be something like text or label, and the output is the data that it can generate. And as I mentioned before, the output space of these two models could be very large. It could be anything depending on the user. And finally, the discriminative model, very likely you're going to get like the output space that is quite limited compared to the previously two types of models. Let's say you have this semantic segmentation, where sometimes semantic segmentation can be seen as generative as well. But usually when there are just foreground, background, or the maybe incoming object, when you limited the output space, then it could be a discriminative task. Classification, object detection, instance segmentation, all of these could be cast as discriminative model, but usually the classification is the one. Usually regression is another one for discriminative model task. I think that's all for this. And yes, these are the models that we will learn in this course. And I'm so sorry, this is more like a typo. Naive Bayes is not going to be learned because it's already learned as a supervised learning task. This is just a typo. So yes, before midterm, we probably cover up until here. And just to recap, we've learned before that these are, let's say, parametric model, and the following are non-parametric model. Okay, Naive Bayes parametric model. This one is parametric model. And we also learned that, let's say, these two actually could be three, are for regression task. And this very last one are classification task, that as well. And the rest which are here are all clustering tasks. So yes, that's what we would cover in this course. Is there anything that I missed? Okay, let's stop the lecture here because my